You are strapped into a seat 200 miles above Earth. The hatch opens. The vacuum outside reads 455 degrees below zero. Your suit is the only thing between you and a place that has killed every unprotected human it ever touched. But here is the part nobody tells you. Space will not freeze you. Space will cook you first. Your radiators cannot keep up. Your shaded side is frostbitten. Your lit side is blistered. 300 degrees of difference across one body. If you enjoy voyages where the physics keeps trying to kill the crew, hit like and subscribe. Strap in. We are leaving the cabin. Here is the part that breaks every new engineer on day one. You're floating in a place that reads 455 degrees below zero. Your onboard computers are running. Your life support is cycling air, your radios are transmitting, and every one of those systems is generating heat that has nowhere to go. Nowhere. That word is doing a lot of work. On Earth, a hot laptop cools because air molecules bump into its fins and carry warmth away. A car engine cools because a pump pushes coolant past a radiator and wind rips the heat off the fins. Both of those tricks need something to touch. A fluid, a gas, a medium. In the vacuum around your spacecraft there is no medium, no air to bump, no wind to strip. The waste heat from every circuit, every motor, every human body on board has exactly one exit route. It has to be radiated away as infrared light, one photon at a time. That is slow, painfully slow. Think about a thermos. A good one keeps your coffee hot for hours because the double wall has a vacuum sealed between the layers. The vacuum stops conduction. The vacuum stops convection. The coffee can only lose heat by radiating it, and radiation is so inefficient that your drink stays warm through an entire workday. Now flip that picture. Your spacecraft is the coffee. The vacuum of space is the thermos wall. You're trapped inside your own insulation. A mission planner sees this before anything else. Before fuel, before food, before radiation shielding. The first line item on a crewed spacecraft's design document is thermal control, and the first problem it solves is not how to stay warm. It is how to dump the heat that the crew and their machines keep making. A human body at rest puts out about 100 watts, roughly the same as an old incandescent bulb. Put 7 astronauts in a pressurized cabin, and you've already lit a 700-watt space heater that never turns off. Add the computers, add the carbon dioxide scrubbers, add the pumps, the fans, the lights, the cameras, the experiments. The International Space Station generates around 70,000 watts of waste heat on a normal day. That is the energy of a small apartment building, stuffed inside an aluminum can with no air around it. The Space Shuttle orbiters carried fluid radiators mounted inside the cargo bay doors. Those doors did not open to unload satellites. They opened because if they stayed shut for more than a few hours in orbit, the crew would start cooking inside the pressurized deck. Mission rules were firm on this point. Doors open within hours of reaching orbit or you come home early. Every spacecraft you have ever heard of lives inside this same trap. The vehicle is a heat source. The vacuum is an insulator. The only way out for that heat is a slow, glowing bleed of infrared into the dark. So when somebody tells you space is cold, they're telling you half of a story. The other half is the engineering nightmare that killed the dream of a quick mission to Mars back in the planning stages. Because the bigger the ship, the harder this problem gets, and the ships getting proposed right now are enormous. Temperature is a trick word in space. On Earth, you learned it meant something obvious. A thermometer dips into a cup of water and a number comes out. Cold water, hot water. The number describes the liquid. Simple. In a vacuum, that definition stops working. Temperature in the strictest physics sense, measures how fast particles are jiggling. Fast particles register as hot, slow particles register as cold. Stop the jiggling entirely and you hit absolute zero, 459 degrees below zero on the Fahrenheit scale, the theoretical floor. Now imagine a region of space with almost no particles in it at all. What is its temperature? The honest answer is that the question barely means anything. With nothing to measure, there is nothing to report. But space is not empty. It is almost empty, which is different. Scatter a few particles into a cubic yard of interstellar vacuum, and they are moving fast. Individually, each one carries real kinetic energy. If you could somehow catch them and add up their jiggle, you would get a surprisingly high number. But there are maybe 10 of them in a volume the size of your bedroom. They could not warm your hand if you stuck it out there for 1,000 years. There are simply not enough of them to matter. So how did we end up with that famous figure of 455 degrees below zero? That number does not come from particles, it comes from light. Everywhere in the universe, in every direction, a faint glow of microwave radiation is washing through the vacuum. It is the leftover warmth from the Big Bang, stretched out by billions of years of cosmic expansion until it cooled down to just 2.7 degrees above absolute zero. Scientists call it the cosmic microwave background. Point a sensitive antenna at the blackest patch of sky you can find, and you will still pick it up, humming at that same frigid temperature. It is the universe's thermal floor. That glow is what sets the coldest temperature any object in deep space can passively reach. If you flew a perfectly insulated probe far from every star, shut off all its electronics, and waited long enough, it would eventually equalize with that background. It would settle at 2.7 Kelvin. That is the coldest gift the universe is willing to give you for free. But here is where mission planners start cursing. Your spacecraft is not in deep intergalactic space. Your spacecraft is near a star. Sunlight is pouring onto it. Planets below are radiating their own infrared back up at it. The local temperature is not the cosmic background number at all. It is a chaotic mess of hot photons slamming into one face of your ship, while the other face stares into the cold background trying to shed heat. A spacecraft in low Earth orbit can see its sunlit skin hit 250 degrees Fahrenheit, while the shaded skin plunges to 250 below. Same craft, same second. 300 degrees spread across a few feet of aluminum. That is what the temperature of space actually means for anybody trying to live out there. It is not a number. It is a war between radiation sources. And in 1971, 3 men learned how fast that war can be lost. 3 cosmonauts boarded the Soyuz 11 capsule in June of 1971. Georgy Dobrovolsky, Vladislav Volkov, Viktor Patsayev. They had just spent 23 days aboard Salyut 1, the first space station humans ever built, running experiments and proving that long-duration orbital work was possible. On the way home, their capsule separated from the station, oriented for re-entry, and began the burn back toward Kazakhstan. Somewhere around 100 miles altitude, a pressure equalization valve popped open early. It was supposed to open low in the atmosphere after the heat of re-entry had passed, so the crew cabin could match outside air pressure before landing. Instead, it opened while they were still in vacuum. All the air inside the capsule rushed out through a hole smaller than a coin. The crew was not wearing pressure suits. Soviet capsule design at the time traded suits for space, because the Soyuz was cramped and 3 men in suits simply did not fit. The cabin itself was supposed to be their suit. For every previous flight, that had worked fine. On this flight, the hole turned the cabin into the vacuum. Telemetry later suggested the men realized what was happening within seconds. They could hear the hiss. They could feel the pressure dropping in their ears. One of them appears to have tried to manually close the valve, a small wheel in an awkward spot behind a seat, but at full decompression, a person loses useful consciousness in 9 to 15 seconds. They did not have time. When the capsule touched down on the step and the recovery team opened the hatch, the 3 cosmonauts were in their couches, no visible injuries, strapped in exactly as they had been for re-entry. Dead. The only humans ever confirmed killed by exposure to vacuum. Autopsies showed what vacuum actually does to a body, and it is worth being precise here because the movies have lied to everyone for decades. The bodies did not explode. They did not freeze solid. Skin did not frost over. Vacuum kills in a quieter way. The gases dissolved in the blood started coming out of solution, the way a shaken soda fizzes when you open it. Oxygen left the lungs. The brain ran out of fuel within a handful of seconds. Hearts kept beating for a minute or two, pumping blood that had no oxygen left to deliver. Then they stopped. The freezing everyone pictures never had time to happen. Heat only leaves a human body by radiation in a vacuum, and radiation is slow. The men would have taken hours to cool to the temperature of their capsule walls. They died of decompression long before the cold was relevant. The Soviet program made 2 changes after Soyuz 11. Crews got smaller, so suits could fit. And pressure suits became mandatory during launch, re-entry, and any high-risk phase of flight. Every crewed spacecraft flying today, Russian, American, Chinese, commercial, follows that rule. The 3 men on Soyuz 11 are the reason. Their capsule had done its job, the heat shield held, the parachutes deployed, the landing was nominal, the spacecraft was fine. But in 1965, a Soviet cosmonaut on the other side of a different hatch had already shown what happens when the suit itself becomes the problem. Alexei Leonov was the first human to step outside a spacecraft. March 18th, 1965. His Voskhod 2 capsule orbited Earth at 17,000 miles per hour, and Leonov climbed out through an inflatable airlock into the vacuum tethered by a 16-foot umbilical. He floated there for 12 minutes and 9 seconds, waving at a camera mounted on the capsule's hull, the first man ever to see Earth with nothing but a helmet visor between him and the sky. Then he tried to go back inside. His suit had been designed to hold pressure against the vacuum, and it was doing that job. What the engineers had not fully modelled was how much the suit would bloat when the only thing pushing back on it was empty space. On the ground, atmospheric pressure kept the fabric snug against his body. In orbit, with no atmosphere at all, the internal pressure pushed outward against nothing. The suit ballooned. His gloves stiffened until he could barely close his fingers. His boots floated off his heels. The whole garment expanded into a rigid humanoid balloon roughly 3 inches larger in every direction than it had been on the launch pad. The airlock hatch was a round opening about 4 feet across. Leonov had squeezed through it going out. Coming back, he could not fit. He did not radio mission control. He later said he was afraid that if he reported the problem, the Soviet political apparatus would turn his emergency into a propaganda disaster. So he solved it himself, alone, outside a spacecraft with his oxygen supply ticking down and his body temperature climbing inside a suit that was not dumping heat fast enough. He opened a valve on his own suit and bled off pressure, deliberately. He dropped his suit pressure below the safe threshold, accepting the risk of the bends to let the fabric soften enough to fold himself back through the hatch. He went in head first instead of feet first, the wrong way, which meant he had to contort inside the airlock to close the outer door. By the time the hatch sealed behind him, his core temperature had risen almost 2 degrees Fahrenheit. His heart rate was over 190, and sweat had pooled in his boots up to his knees. The cooling system in his suit could not keep up with a working man in direct sunlight. His body was trying to radiate heat through fabric into vacuum and losing. This is the part most retellings skip. Leonoff's near death was not just about a ballooned suit. It was about thermal control failing at the same moment as mechanical control. He was cooking inside an oven that would not let him out. The Soviets kept the full story classified for decades. When Leonov finally described it in public, Western engineers already knew the principle from their own close calls. Any garment you send into space is fighting 2 wars at once. It has to hold pressure against the vacuum without inflating like a parade float. And it has to shed a working human's body heat using nothing but radiation and a trickle of circulating water. Modern suits use liquid cooling garments, skin-tight layers threaded with tubes of chilled water that run over the astronaut's skin and carry heat out to a sublimator that vents it to space. The design exists because of Leonov's sweat-filled boots, but water cooling only works if the water keeps flowing, and in 2013, a spacewalker named Luca Parmitano would find out what happens when it does not. Before we get to him, we have to talk about why heat is so hard to get rid of in the first place. Because on your desk, it is easy. In orbit, it is the mission. Pop the hood on a running car and put your hand near the radiator. You will feel the wind rushing through the fins, air molecules picking up heat from hot metal and hauling it away by the billions every second. That is convection doing the brute force work. Behind it, conduction moves heat from the engine block into the coolant, then from the coolant into the radiator fins. 3 kinds of heat transfer, all cooperating, all free, because Earth gave you an atmosphere. Take that same engine and put it in orbit. 2 of the 3 mechanisms die instantly. Conduction needs matter in contact. It works fine inside the spacecraft, moving heat from a hot chip to a cold plate through solid metal. It stops working the moment the heat reaches the outer hull, because there is nothing touching the hull from outside. The aluminum skin sits against nothing. Nothing takes the next step. Convection needs a fluid that can circulate. Hot air rises, cool air sinks, and the motion carries warmth. In vacuum there is no fluid to circulate, so convection does not happen at all. This is also why a flame in orbit does not flicker upward the way it does in your kitchen. Without convection, the hot gases do not rise. A candle in zero gravity burns as a small blue sphere and chokes itself on its own combustion products. That leaves radiation, the slow one. Every warm object glows in the infrared. Your body does it right now. So does your coffee mug, your laptop, the walls of your room. On Earth you never notice because convection and conduction are doing most of the work, shedding heat so efficiently that the slow, radiative leak is a rounding error. In orbit, radiation becomes the whole budget. Every watt of waste heat your spacecraft generates has to leave as infrared photons, emitted from the craft's outer surface, streaming off into the dark. The physics of radiative cooling is brutal. The rate at which a surface can dump heat depends on 2 things: its emissivity, which is basically how good it is at glowing in the infrared, and its temperature raised to the 4th power. That 4th power is the killer. If you want to reject twice as much heat from a surface, you do not need twice the surface area. You need either a lot more area, or you need that surface running significantly hotter. Cold radiators barely radiate at all. Hot radiators radiate well, but hot radiators inside a spacecraft are exactly what you are trying to avoid. Engineers solve this by pumping working fluid out to big external panels, letting the fluid dump heat from the panel surface and circulating it back. The International Space Station uses ammonia, which stays liquid across a wider temperature range than water and can carry more heat per pound. The ammonia picks up waste heat from the crew modules through a series of heat exchangers, flows out through insulated lines into 8 giant radiator panels that unfold like aluminum wings, radiates the heat into space, and comes back cooler to start the cycle again. The panels are enormous. Each one measures roughly 75 feet long. Combined, they provide over 2,700 square feet of radiating surface. That is more than the floor area of a large family home, bolted to the outside of the station, doing nothing but glowing in the infrared to keep the crew from boiling in their own metabolism. And every single one of those panels is a vulnerability. A pinhole leak in the ammonia lines and the coolant vents to space. A micrometeoroid strike through a radiator tube and that loop is dead. Station crews have run emergency repairs on the ammonia system more than once. During Apollo, the solution was simpler. Nobody had room for huge radiators on a capsule going to the moon, so the capsule spun. The Apollo command and service module looked like a cone glued to a can, small enough that 2 radiator panels bolted to the service module's side were all the engineers could spare. Those radiators worked fine when they were facing cold space. They did not work at all when they were facing the sun, and on a 3-day coast out to the moon, one side of the spacecraft would be in sunlight for the entire trip unless somebody did something about it. So the flight controllers kept it turning. They called it passive thermal control. The crews called it the barbecue roll. Apollo spacecraft on their way to the moon would fire attitude thrusters to start a slow rotation around the long axis of the vehicle, about 3 revolutions per hour, and then coast. Just spin, turn. The whole cone and cylinder stack rotating like a chicken on a rotisserie, so that every face of the spacecraft got roughly equal time in sunlight and equal time in shadow. If they had not done that, the sunlit side would have climbed toward 250 degrees Fahrenheit. The shaded side would have plunged to 250 below. Propellant lines running from one end of the service module to the other would have boiled at one end and frozen at the other. Fuel would have separated from oxidizer in ways the valves were not built to handle. Electronic boxes mounted on the warm side would have cooked. Electronic boxes on the cold side would have contracted, cracked seals, failed. The spin kept everything averaged out. Every square inch of the spacecraft got a slow alternation of hot and cold instead of a permanent hot or cold sentence. The temperature swings were small enough that the thermal control system could handle them with passive insulation and a few small heaters for the coldest components. Here is what a mission planner notices about this solution. The Apollo program, the most technically ambitious thing humans had ever done, solved its thermal control problem by treating the spacecraft like meat over a fire. The engineers were not embarrassed, they were proud. It was simple, it used almost no power, and it worked every single mission from Apollo 7 through Apollo 17. The trick only works for certain shapes. A long, roughly symmetrical stack like Apollo can spin around its axis without affecting anything important. A large asymmetric spacecraft with big solar arrays, directional antennas, and science instruments that all need to point different directions cannot spin like that. The International Space Station, for example, holds a fixed attitude relative to its orbital path. Its antennas need to track ground stations. Its solar arrays need to track the star. Spinning would destroy those pointing requirements. So the station pays the cost in different coin. It carries those big ammonia radiators we just walked through, because it cannot use the Apollo trick. Parker Solar Probe cannot use the trick either, for a much more dramatic reason. Parker is doing something no other spacecraft has ever done. It is flying directly into the outer corona of the star it was sent to study, closer than any human-made object has ever been. At closest approach, it passes within about 4 million miles of the stellar surface, through a region where the ambient radiation field is intense enough to vaporize aluminum. Spinning would not save Parker. Parker needs to point one very specific thing at the star at all times, and hide everything else behind it. That one thing is a shield, and the shield runs hot enough to melt steel while the spacecraft just inches behind it, keeps its instruments at room temperature. Parker Solar Probe launched in August of 2018 on a 7-year mission of repeated close passes at the star. Every orbit takes it in a little tighter. The closest passes yet have brought it within about 3.8 million miles of the stellar surface, a distance where the intensity of sunlight is around 475 times stronger than what a spacecraft feels in Earth orbit. At that range, an unprotected aluminum surface would hit roughly 2,500 degrees Fahrenheit in seconds. Aluminum melts at around 1,200. The spacecraft would be a puddle before it finished the sentence, so Parker does not use aluminum for the parts that face the star. It uses a shield. The shield is officially called the Thermal Protection System. It is a hexagonal slab about 8 feet across and 4.5 inches thick, mounted on the sunward end of the probe like the round part of a lollipop. The core of the slab is carbon foam, chosen because it is almost entirely empty space, mostly air pockets between a lacework of carbon struts. Low density means low thermal mass. The shield can get extremely hot on its outer face without conducting much of that heat back through its own body. The front face of the shield, the side looking straight at the star, gets coated with a white alumina ceramic layer. White, because white surfaces reflect more of the incoming radiation than dark ones. The shield still soaks up enormous energy, but it rejects a huge fraction of it back out into space before it can cook anything behind it. At closest approach, that white face climbs to around 2,500 degrees Fahrenheit. The back face of the same shield, 4.5 inches away, sits at about 85 degrees, room temperature. Every instrument on the spacecraft lives in that 85-degree shadow. They are taking measurements of a stellar atmosphere hotter than any fire humans have ever lit, and they're doing it at office building temperature. The engineering here depends on precision pointing. If Parker ever lets its shield drift more than a few degrees off the star, the edge of the spacecraft peeks around into direct sunlight and immediately starts heating. There are no second chances at that distance. The attitude control system uses 4 small reaction wheels and a set of thrusters to keep the shield locked onto the star within a tight tolerance, continuously, even while the solar wind and radiation pressure push on the spacecraft from unpredictable angles. The solar arrays cannot hide behind the shield. They need sunlight to work, and Parker is drinking from a fire hose of it. The arrays are mounted on hinged booms that let them retract almost entirely behind the shield during the closest passes, exposing just a sliver of their surface to the star. That sliver produces more power than the arrays would in Earth orbit, because of how much more intense the radiation is at that range. Behind the sliver, a water cooling loop pulls heat off the panels and carries it to small radiators hiding in the shield's shadow. Water as a coolant, on a probe flying through the outer corona. The same stuff in your kitchen sink, doing the job of keeping solar panels alive inside one of the hottest places any machine has ever been. Parker is a beautiful example of one side of the thermal problem, shielding from external heat. On the other side sits a problem that never goes away no matter how good your shield is. Heat made inside the spacecraft. The crew, the computers, the carbon dioxide scrubbers. And when one side of a ship stares at a star while the other stares into the dark, the asymmetry of what happens next becomes its own kind of nightmare. Point any spacecraft at a star and hold it still. Wait an hour. The side facing the star climbs toward 250 degrees Fahrenheit. The side facing away plunges toward 250 below. 300 degrees of temperature difference, stretched across a vehicle that might only be 15 feet wide. The metal skin is now under stress that no terrestrial structure ever sees. It wants to expand on the hot side, it wants to contract on the cold side. It cannot do both. Thermal engineers call this the gradient problem, and it is one of the most stubborn challenges in spacecraft design. Aluminum expands and contracts with temperature. A strip of aluminum 6 feet long will stretch or shrink by about a 50th of an inch for every 100-degree swing in its temperature. That sounds small. Now imagine a spacecraft hull where one side is 300 degrees hotter than the other. The hot side is trying to be longer than the cold side by a full 1/10 of an inch. The structure cannot allow that, so it bends. A satellite watching the stars needs its telescope pointed precisely. A communications dish needs its reflector shaped correctly. A solar array needs its panels flat. Every one of those components goes slightly out of shape when one side sees a star and the other side sees space. Engineers spend entire careers modelling these distortions and designing around them. Mirrors get mounted on flexures that can absorb a tiny bit of warping without transmitting the stress to the optics. Dishes get machined out of materials with absurdly low thermal expansion, usually carbon composites or a nickel-iron alloy called Invar that barely moves at all. The gradient problem gets worse the longer a spacecraft sits in one attitude. Apollo spun to average it out. The space station rotates instruments on gimbals and accepts some distortion. Deep space probes that need to hold a fixed pointing for months sometimes use internal heaters to deliberately warm their cold side, burning precious electricity just to keep the structure from bending. Now make it worse. Add a crew. A pressurized module in orbit has a hot side and a cold side just like any satellite. The metal skin on the sunlit face is much warmer than the skin on the shaded face. But inside the module the air is supposed to stay at a livable 72 degrees across the entire volume. The inside of the hot wall is trying to radiate heat into the cabin. The inside of the cold wall is trying to steal heat from the cabin. Crew members sleeping near a cold wall wake up shivering. Crew members floating near a hot wall feel a slow bake from behind. Fans blow constantly to mix the air, because without convection to move warm air around, pockets of temperature would just sit there the way they do in a freezer. A typical crew module wraps its exterior in multi-layer insulation, a stack of shiny plastic sheets, usually somewhere between 15 and 25 layers, each one coated with aluminum. Each layer reflects most of the thermal radiation that tries to pass through it. The stack as a whole behaves like a vacuum thermos wall, radically slowing the heat transfer in either direction. With good insulation, the inside of the pressure hull stays close to cabin temperature, regardless of what the outside skin is doing. The insulation does not solve the problem, it just moves it. Now the heat the crew generates has to get through that same insulation on its way out, or it has to be routed to a specific dump point. That is why every crewed spacecraft has specific radiator zones, concentrated patches of surface, where the insulation is deliberately left off and the heat is funneled out. The rest of the hull is wrapped up tight. The radiators are exposed and cold. Fluid loops carry the waste heat from inside the cabin out to the exposed zones, and the zones do the actual dumping. On a small craft like a Dragon capsule, This is manageable. On something the size of a space station, with 70,000 watts of waste heat to reject every minute, the zones have to be enormous, and the biggest crude object humans have ever built is sweating that heat out through ammonia pipes right now, about 250 miles overhead. The International Space Station is roughly the size of a football field from end to end. It has a pressurized volume about the same as a 7-bedroom house. 7 astronauts live there full-time. Scientific experiments run around the clock. Computers, life support, lighting, communications, and the waste heat from all of it adds up to around 70,000 watts in steady state. The station has to dump every single watt continuously into the dark. The system that does this is called the External Active Thermal Control System, and it is one of the largest engineering projects ever built off the ground. 2 independent loops carry ammonia through the station's exterior. Each loop has its own pumps, its own reservoirs, its own radiator panels. The redundancy is not optional. If either loop fails, the station loses half its cooling capacity, and major systems have to shut down within hours to avoid overheating. A total cooling failure would force an evacuation. The ammonia starts its journey inside the pressurized crew modules. It does not enter the modules directly, because ammonia is toxic, and a leak into the cabin air would kill the crew quickly. Instead, a separate water loop circulates inside the modules, picking up waste heat from the avionics, the air, and anything else that needs cooling. That water flows to an interface heat exchanger mounted on the outside of each module, where the heat crosses into the ammonia without the 2 fluids ever mixing. The ammonia then flows out through insulated lines to the truss, the long backbone of the station, and from the truss out to the radiator panels. The panels are the 8 huge wings jutting from the station's exterior. Each one is about 75 feet long and 12 feet wide. Combined, they expose over 2,700 square feet of radiating surface to space. The panels are painted with a white coating that is specifically tuned to absorb very little sunlight while emitting infrared efficiently. This balance matters. A black radiator would dump heat well, but also soak up enormous amounts of incoming solar energy every time it rotated into sunlight. The white coating reflects most of the sun's visible light while still glowing in the infrared. The panels rotate. They have to. As the station orbits Earth every 90 minutes, the angle of sunlight changes constantly, and the radiators need to be edge-on to the star whenever possible to minimize solar heating. Motors driven by the station's guidance computers continuously steer the panels to keep them cold. In 2013, one of the ammonia pumps failed. The cause was traced to a flow control valve that had begun behaving erratically, and the failure forced flight controllers to reroute cooling through the remaining loop while a spacewalk repair was organized. 2 astronauts spent over 7 hours outside the station, swapping out a refrigerator-sized pump module, working in gloves so stiff that their hands cramped within the first hour. They had to disconnect ammonia lines, let the fluid vent into space as a white crystal plume, and connect new lines without contaminating the system. If the pump had failed in a way that lost the loop entirely, the station might have had to be partially evacuated while repairs were arranged. The ammonia system is the station's single most fragile life-critical component. A micrometeoroid could hole a radiator panel in a microsecond. A valve could stick, a pump could seize. Every mission plan since the station's construction has included contingencies for partial thermal failures, and those contingencies all ultimately end the same way. Reduce power, shut down experiments, cool down. The crew aboard the station knows this, which is why, in 2013, when a suit malfunction turned a routine spacewalk into a near drowning, the first thing the crew did was get their colleague back inside. Luca Parmitano was 90 minutes into a spacewalk on July 16, 2013, when he felt something cold on the back of his neck. It was the beginning of one of the most dangerous incidents in the history of the International Space Station, and the story of how it unfolded is still required reading in every astronaut training program. Parmitano was working outside the station with fellow spacewalker Chris Cassidy, running a cable installation that had been planned for weeks. The cold sensation on his neck was unusual but not alarming at first. Spacesuits feel strange in ways astronauts learn to accept. Every movement creates pressure shifts inside the garment. Cooling tubes sewn into the liquid cooling garment can cause localized chills. Parmitano mentioned it to mission control and kept working. Then the water spread. Within minutes, a thin layer of liquid was creeping across the back of his head, up and over the crown down toward his face. In zero gravity, water does not drip. It clings. It forms sheets and droplets that hold their shape and slide along whatever surface they find. The water inside Parmitano's helmet was finding the contours of his head and creeping around it the way oil would spread across a windshield. Mission Control told him to end the spacewalk and return to the airlock. Cassidy, working on a different task, was not initially aware of how bad the situation was. Parmitano began making his way back along the station's handrails, pulling himself hand over hand while the water kept coming. By the time he reached the airlock door, water was covering his eyes. He could not see. It was in his ears. It had started to pool around his nose and mouth. He couldn't speak clearly because every time he tried, water sloshed into his mouth. Inside a helmet in zero gravity, a person can drown. There is no way to shake the water off. There is no way to clear it. It simply sits there, slowly covering every airway until there is no breathable space left. Parmitano later said he navigated the last part of the walk from memory, following the feel of the handrails with his gloves because he could no longer see them. He found the airlock by touch. He got inside. The hatch closed. Pressure was restored. Cassidy helped pull the helmet off, and almost a quart and a half of water spilled out of it in a glittering zero-gravity cloud. The cause was traced to a clogged water separator in the suit's life support pack. The separator was supposed to extract water from the cooling system's exhaust gas and route it away from the helmet. When it clogged, water backed up into the ventilation line and was pumped straight into Parmitano's helmet under pressure. The suit had been doing its job. It was circulating chilled water through the cooling garment to keep him from overheating while he worked. Spacewalks generate enormous metabolic heat. An astronaut in a pressure suit moving tools, bracing against handrails, exerting muscles to force stiff gloves closed around bolts, can generate 2,000 watts of body heat. Without aggressive cooling, he would be incapacitated by heat stroke within an hour. Parmitano's suit was keeping him cool right up until the moment the same cooling system started drowning him. After the incident, NASA redesigned the separators and added a water-absorbent pad at the back of every helmet as emergency capacity, plus a snorkel-style breathing tube connected to the suit's dry chest area. But the deeper lesson was harder. Every system that keeps a crew alive in space is a potential killer, and as spacecraft get bigger, those systems multiply. Here is a rule that every mission planner learns early, and it is the rule that keeps killing proposals for big interplanetary ships. The waste heat a crewed spacecraft generates grows roughly with the volume of the vehicle. More volume means more crew, more equipment, more life support, more experiments, all running in parallel. The amount of radiator surface area available to dump that heat grows with the square of the vehicle's size. Volume goes as the cube, surface area goes as the square. The cube grows faster. This is the surface-to-volume trap, and it is the same geometry that makes elephants overheat faster than mice. A small animal has tons of skin per pound of body. A big animal has less. In the animal world, this is why whales live in cold water and shrews live in mud burrows. In the spacecraft world, it is why the bigger ships are the hardest to keep cool. Double the length of a spacecraft and you multiply its internal volume by 8, but its skin, the surface that can radiate, only multiplies by 4. The ship gets twice as hard to cool just from being bigger. More crew inside generating more metabolic heat. More electronics running more systems. Same problem, compounded. The International Space Station gets away with it by unfolding radiators that are much larger than its hull. Those 8 panels on the truss are essentially extra surface area glued onto the outside of the ship. Without them, the station's own skin could not possibly dump 70,000 watts of waste heat. The panels extend the radiating area far beyond what the pressurized volume would allow. Now scale up. Consider a proposed Mars transit vehicle carrying a crew of 6 for 9 months of interplanetary coast. Such a ship needs more pressurized volume than any space station has ever had, because the crew has to live, exercise, eat, sleep, and store supplies for the entire journey. It also has to carry a reactor or large solar arrays for power, along with propulsion systems, communications, navigation, life support, and radiation shielding. Each of those subsystems generates heat. Current NASA mission studies for crewed Mars transit vehicles estimate waste heat loads in the range of 25 to 50 kilowatts, depending on the architecture. A few studies looking at nuclear electric ships estimate far higher. The radiator area needed to dump 50 kilowatts into deep space at a reasonable radiator temperature is on the order of 1,000 square feet. That is roughly the size of a small apartment, all of it dedicated to nothing but glowing in the infrared. And it has to unfold from a launch configuration, survive the vibration of liftoff, deploy without jamming, and work perfectly for years in a radiation environment that degrades every material humans can manufacture. The bigger the ship gets, the worse this scales. A true colonizing vessel, the kind of ship that science fiction loves to draw. The kind with a spinning habitat ring and hundreds of crew aboard would need radiator surfaces measured in acres. The drawings you see in illustrations almost never show those radiators, because the artists know they would dominate the entire vehicle and ruin the silhouette. Real engineering drawings of the same concepts are covered in them. Fins, panels, huge flat wings that have to track perpendicular to the star at all times, rotating as the ship rotates, extending and retracting to manage the thermal load. A mission planner looking at any of these concepts asks the radiator question first, not the fuel question, not the food question, not the propulsion question, the radiator question. Because if the answer does not close, nothing else matters. The crew will cook before they run out of anything else. Telescopes trying to see the dimmest, coldest objects in the universe face the same problem in reverse. They cannot afford to be warm, and one of them found a way to beat the trap entirely. The James Webb Space Telescope cannot see what it was built to see unless it is freezing. Webb's instruments detect infrared light, which is essentially heat radiation. Warm galaxies glow in the infrared. Warm planets glow in the infrared. Warm stars glow in the infrared. The problem is that a warm telescope also glows in the infrared, and if the telescope is warmer than the things it is trying to observe, its own thermal emission swamps the signal. Looking for distant galaxies with a warm infrared telescope is like trying to hear a whisper while standing next to a jackhammer. The instruments have to be cold, not a little cold, deep cryogenic cold. The near-infrared cameras need to operate at around 39 degrees above absolute zero. The mid-infrared instrument needs to get even colder, around 7 degrees above absolute zero, about 447 degrees below zero on the Fahrenheit scale. That is colder than the vacuum of space itself, colder than almost anywhere in the universe, except specific exotic objects. Webb achieves these temperatures passively, mostly. The trick is a sunshield. The sunshield is 5 layers of a material called Kapton, a polymer film coated with a thin layer of aluminum. Each layer is roughly the thickness of a human hair. The 5 layers together weigh less than 300 pounds, and when fully deployed they form a kite-shaped shade about 70 feet long and 46 feet across, bigger than a tennis court. The shield is stretched taut with gaps between the layers. The gaps are essential. If the layers touched, heat would conduct from the hot side straight to the cold side. With the gaps in place, each layer has to radiate its heat to the next layer through the vacuum between them, and then that layer has to re-radiate to the next, and so on. Each handoff sheds a huge fraction of the heat as it goes. The result is a cascade. The outermost layer of the shield, the one facing the star, climbs to around 250 degrees Fahrenheit. The next layer sits cooler, the next cooler still. By the time you reach the 5th layer, the one closest to the telescope, the temperature has fallen to roughly minus 370 degrees. The sunshield drops the temperature by more than 500 degrees across its thickness, using nothing but 5 sheets of plastic and the vacuum of space. No refrigerant, no moving parts, no electrical power. Pure radiative physics, arranged with exquisite precision. Behind the shield, the telescope sits in permanent shadow, free to radiate its own heat into the cold of space on the backside. With the hot star completely blocked, Webb cools itself simply by glowing. Its primary mirror settles at around 40 degrees above absolute zero. Most of its instruments reach their operating temperatures just by sitting there and waiting. Deploying the shield was the riskiest part of the entire Webb mission. The 5 layers had to unfold from a launch-packed bundle into their final tension geometry, using 140 release mechanisms, 400 pulleys, 90 cables, and 8 motors. Every one of those steps had to work perfectly. Any single failure would have doomed the mission. During testing on the ground, one early prototype of the shield tore. Another had fasteners come loose. The final flight version deployed flawlessly in January of 2022, and Webb has been operating at cryogenic temperature ever since. Webb could not have done any of this in low Earth orbit. It is not there. It is about 1 million miles from our planet, at a very specific location where the thermal environment is perfect. That location is called the second Lagrange point, and it is the coldest parking spot in the inner solar system. The second Lagrange point, usually written as L2, is a gravitational balance point about 1 million miles from Earth in the direction directly opposite the star. Gravity from the star and gravity from Earth combine in just the right way that a spacecraft parked at L2 orbits the star with the same period that Earth does, staying roughly in line with Earth, which means it moves in lockstep with our planet around the star. From a thermal engineering standpoint, L2 is the best real estate in the inner solar system. From any point on the Earth-facing side of L2, the star and Earth appear in nearly the same direction. If you build a spacecraft with one face pointing toward that direction and the other face pointing away, the sunward face is always pointed at the star and at Earth simultaneously, and the anti-sun face is always pointed at cold, dark, empty space. No orbital rotation changes this. No seasonal shift changes this. The geometry is static. Put your radiators on the anti-sun side, and they will see nothing but the cosmic background radiation for the entire mission. This is why Webb went to L2. It is why the Herschel Space Observatory went to L2. It is why the Planck mission that mapped the cosmic microwave background went to L2. It is why the European Space Agency's Euclid telescope is there now, and why the upcoming Nancy Grace Roman Space Telescope is heading there. L2 gives a passively cooled infrared instrument exactly what it needs: a permanent hot side and a permanent cold side, arranged by the geometry of the solar system itself. A spacecraft in low Earth orbit, by contrast, orbits the planet every 90 minutes. It spends part of each orbit in direct sunlight, part in Earth's shadow, and part crossing the day-night terminator where solar heating changes minute by minute. Its thermal environment is a sawtooth wave. Every orbit it heats up, every orbit it cools down, every orbit its radiators rotate through a range of angles relative to the star. Materials expand and contract with every cycle. Over thousands of orbits, this thermal cycling causes fatigue in solar array hinges, in radiator joints, in any mechanism with moving parts. Hubble, which is in low Earth orbit, has experienced exactly this. Its original solar arrays, made of a sandwich material with different thermal expansion coefficients on different sides, began to flex and twist with every orbital day-night cycle. The flexing vibrated the entire telescope and blurred its observations. A servicing mission had to replace the arrays with a stiffer design. L2 telescopes do not face this problem at all because they never enter Earth's shadow. They never see a day-night cycle. Their thermal environment is as stable as any environment a spacecraft can find. The cost of L2 is distance. A probe at L2 is about 4 times farther away than the Moon. Round-trip communications take about 10 seconds. Repair missions are impossible with current technology. If something breaks at L2, it stays broken. This is why Webb's deployment had to work perfectly. There was no option to send a crew out there to fix it. L2 also has a subtle thermal catch. Although the position is geometrically perfect, a spacecraft parked exactly at L2 would be permanently in Earth's shadow for communications, but also in a location that is gravitationally unstable. Real missions orbit in halo paths around L2, loops that keep them close to the ideal point without actually sitting on it. Those halo orbits take the spacecraft slightly above and below the Earth-star line over the course of about 6 months, which means the thermal environment is not perfectly static after all. It shifts slightly with the orbit. Engineers have to plan for these variations, and the sunshield has to be oversized enough to keep the cold side shaded even when the geometry drifts. For all that, L2 is as close to free cryogenic cooling as the universe will let a spacecraft get. But even free is not cold enough for every instrument. Webb's 4 main instruments all sit behind the sunshield. 3 of them reach their operating temperatures passively, just by radiating their own heat into cold space. The near-infrared camera cools to about 39 degrees above absolute zero. The near-infrared spectrograph cools to about the same. The fine guidance sensor cools to about the same. The 4th instrument, the mid-infrared instrument known as MIR, needs to be colder. MIRI observes longer infrared wavelengths than the other instruments. It sees thermal emission from cool objects, the kind of emission that other instruments cannot pick up, because it requires detectors that are sensitive to much lower energies. To register those weak signals without being drowned out by the instrument's own thermal noise, MIRI has to run at around 6.7 degrees above absolute zero. That is about 447 degrees below zero on the Fahrenheit scale. Passive cooling cannot get there. Behind a perfect sunshield at L2, with radiators optimized for the coldest possible infrared emission, an instrument can passively settle at roughly 35 to 40 degrees above absolute zero. That is the practical flaw. Below that, the background radiation from every nearby surface, from the faint glow of the sunshield itself, from scattered infrared coming off the rest of the spacecraft, prevents further cooling. A passive radiator cannot emit its way below the temperature of everything it can see, because every surface around it is also glowing, and those glows come in as incoming radiation that heats the radiator back up. MIRI needs to beat that flaw by a factor of about 6, and the only way to beat it is to spend energy. The solution is a mechanical cryocooler, an active refrigerator bolted into the spacecraft. Webb's cryocooler uses the same basic physics as your home refrigerator, with enormous technical refinements to let it run for years in space without failing. Helium gas is compressed by pistons, cooled in stages using the vacuum of space as a heat sink, expanded through pulse tubes that extract work from the gas as it flows, and finally forced through a narrow valve where the Joule-Thomson effect cools it still further. The final cold helium is piped to a cold head bolted to MIRI, where it absorbs the instrument's waste heat before being pumped back through the cycle. The pistons are the weakest link in the system. Pistons move. Motion wears out seals. Motion creates vibration. A vibrating instrument cannot take crisp infrared images because the jitter smears the signal. Webb's engineers designed the cryocooler with opposed pistons that cancel each other's motion, leaving almost no net vibration reaching the instrument. The whole system has been running continuously since early 2022, holding MIRI at its operating temperature across millions of observation seconds. If the cryocooler fails, MIRI is done. There is no backup. The other 3 instruments will continue to function, but the unique science MIRI provides, mapping the coldest, dustiest objects in the universe, would stop. Every active cooling system on a long-duration spacecraft is a risk. Mechanical coolers are proven technology with decades of heritage, but they are still single points of failure. Some missions try to avoid them entirely by carrying stored cryogens, tanks of liquid helium or solid hydrogen that gradually boil off to keep instruments cold. Those missions have a hard end date. When the cryogen runs out, the mission is over. The Herschel Space Observatory ended its mission in 2013 for exactly this reason. It ran out of liquid helium and warmed up. Its instruments could no longer function, and the spacecraft was parked in a disposal orbit. Webb chose the cryocooler path specifically to avoid the hard end date. It can, in principle, run for decades as long as power keeps flowing and the pistons keep moving. But heat rejection is the same story regardless of which cooling approach a mission picks. Shed the waste heat or die. And on long missions, the radiator is always the hardest part. Every mission planner who has ever designed a deep space spacecraft ends up frustrated with radiators. They do not care about the ion drive. They do not care about the propellant tanks. They want to talk about radiators, because radiators are always the problem. A radiator has one job: take waste heat from inside the spacecraft and glow it away. That sounds easy until you realize how much radiator area a serious mission actually needs. Rejecting 1 kilowatt of waste heat at a panel temperature of about 80 degrees Fahrenheit requires around 10 square feet of radiating surface, assuming the panel has good emissivity and a clear view of cold space. The numbers look manageable at that scale. A small scientific satellite with a few hundred watts of waste heat can fit its radiators onto the spacecraft hull with room to spare. Now scale up. A A crewed Mars transit vehicle generates roughly 30 to 50 kilowatts of waste heat in steady operation. Using the same math, that works out to 300 to 500 square feet of radiator, maybe more if the panels run cooler than ideal. A nuclear electric ship with a large reactor for propulsion might generate hundreds of kilowatts of waste heat from the reactor alone, on top of the crew and life support load. A reactor producing 1 megawatt of electric power typically needs to reject 2 to 4 megawatts of waste heat, because no reactor is 100% efficient and the leftover energy has to go somewhere. Radiator area for that kind of load climbs into the thousands of square feet. And here is where the paradox kicks in. The best way to make a radiator reject more heat is to run it hotter, because radiative emission scales with temperature to the 4th power. A radiator at 400 degrees Fahrenheit sheds heat much faster per square foot than a radiator at 80 degrees. If you can push your radiator temperature up, you can shrink the panel area dramatically. A factor of 2 hotter radiator gives you roughly 16 times more heat rejection per square foot. But crew cabins cannot run at 400 degrees, neither can most electronics. The heat inside the spacecraft is produced at roughly cabin temperature. To push a radiator to 400 degrees, you need a heat pump to move the heat from the low temperature source up to the high temperature sink, the same way a refrigerator moves heat from inside the cold box to outside the warm kitchen. Heat pumps cost energy. Running one to push your radiators hotter adds to the power budget, which adds to the waste heat, which adds to the radiator load, which was the thing you were trying to fix. Engineers end up in a balancing act. High temperature radiators for reactors, medium temperature loops for electronics, low temperature loops for the crew cabin, each with its own set of panels, plumbing, pumps and control logic. A serious interplanetary ship looks from the side like a porcupine of radiating fins at different temperatures, all running in parallel, all fragile, all critical. Skin in the game mission studies show how quickly the problem can strangle a concept. Proposed nuclear electric Mars tugs from the 2010s routinely devoted 30 to 40% of their total mass to thermal control hardware. Radiator panels outweighed propellant tanks. Pumps and heat exchangers outweighed life support. The ship was less an interplanetary vehicle and more a flying radiator with some incidental cargo attached. NASA's own Mars design reference missions flag thermal control as one of the top 3 technology risks, alongside radiation shielding and long-duration life support. The radiators always seem to need more area than the vehicle configuration allows. The panels always seem to need to be larger than launch vehicles can fit in one piece. Every proposed long-duration spacecraft has to solve this. Nobody has solved it cleanly. The Space Shuttle tried a creative workaround, using hardware that was already on the vehicle for a different purpose, and it got the program through 30 years of orbital missions. Space Shuttle missions had a rule that the cargo bay doors had to open within a few hours of reaching orbit. Every mission. No exceptions except in true emergencies where the crew was coming home immediately. The rule was not about cargo. The rule was about not cooking the crew. The cargo bay doors of the Space Shuttle orbiter were not just garage doors for releasing satellites. The inner surfaces of those doors, the surfaces that faced the cargo bay when the doors were closed and the open sky when the doors were open, were lined with the shuttle's main radiator system. 1,700 square feet of radiating surface split across 8 panels mounted on the insides of those doors. When the doors opened, the radiators deployed with them and saw cold space directly. When the doors were closed, the radiators were trapped inside the payload bay, radiating nothing. The The shuttle generated roughly 21,000 watts of waste heat during normal orbital operations. Crew, avionics, fuel cells producing electricity by combining hydrogen and oxygen, life support systems, and every piece of equipment running in the cabin all dump their heat into the shuttle's central fluid loop. That loop, filled with Freon, carried the heat to the radiators on the cargo bay doors. The Freon circulated through more than 5,500 feet of tubing embedded in the radiator panels, shedding its heat as it flowed, and returned cool to the cabin heat exchangers. With the doors closed, there was nowhere for the Freon to dump its heat. The fluid would recirculate through the cabin loop, picking up more and more thermal energy, and cabin temperature would rise steadily. Within hours, the crew would be in an uncomfortable environment. Within a day, they would be in serious thermal distress. The shuttle had secondary cooling systems for emergencies, evaporators that could dump heat by sublimating ice to the vacuum, but those systems used consumable water and could not sustain the full thermal load indefinitely, so the doors opened, always. The flip side of this arrangement was that the shuttle could never close its doors in orbit, except for a brief window to repressurize the bay for returning satellites or other operations. The vehicle could only return to Earth with the doors closed, because the doors had to be latched for re-entry to protect the radiators from the heat of atmospheric friction. If the doors failed to close, the mission could not come home. Multiple shuttle missions over the years had door latching issues that forced extended troubleshooting on orbit. At least one had a latch that would not engage correctly, and required crew members to manually crank it closed before re-entry could be attempted. The design had another cost. Because the radiators were on the cargo bay doors, the shuttle had to be kept in an orientation where the open bay pointed away from the star during most of its mission. Pointing the open bay at the star would flood the radiators with sunlight and destroy their ability to reject heat. Flight controllers constantly monitored her attitude to keep the bay in shadow. The whole system was an elegant compromise between hardware mass and thermal performance. The shuttle could not afford to carry dedicated deployable radiator panels separate from its cargo bay hardware. So the cargo bay doors did double duty. They protected the payloads during launch and re-entry, and they served as the vehicle's entire thermal radiator system during the mission. 2 jobs, 1 piece of hardware, and it worked for 135 missions. Not a single shuttle was ever lost to a thermal control failure. The fluid loops, the radiators, the pumps, the valves, all held up through decades of operation. The same cannot always be said for smaller, simpler spacecraft. 1 meteoroid, 1 impact, 1 hole, and years of planning end in a thermal emergency. A micrometeoroid is a grain of interplanetary dust, usually smaller than a grain of sand, travelling at speeds of up to 50,000 miles per hour relative to a spacecraft. When one of those grains hits a surface, it does not bounce, it vaporizes. The impact turns the grain and a small crater of the surface into a plume of superheated plasma that blasts outward, sometimes punching clean through thin materials. Radiator panels are thin materials. The International Space Station's ammonia radiators are constructed with thin aluminum face sheets over honeycomb cores, with ammonia flow channels embedded in the honeycomb. A thicker armour would make the panels too heavy to launch. The face sheets are just thick enough to handle internal ammonia pressure and to survive most micrometeoroid impacts. Most, not all. The station's external surfaces get hit by detectable impacts several times a year. Most of those impacts leave small craters that do no functional damage. Occasionally an impact hits a radiator line. In 2017, flight controllers noticed a slow ammonia leak in one of the station's external cooling loops. The leak was traced to a suspected micrometeoroid puncture of a radiator line. The loop was isolated and the affected panel taken offline, reducing overall cooling capacity until a repair could be scheduled. Spacewalk crews have had to manage multiple such leaks across the station's operational life. A radiator leak is one of the quietest emergencies on a spacecraft. No alarm rings at the moment of impact. The spacecraft keeps flying normally. Telemetry shows nothing immediately wrong. The first sign is often a slow drop in coolant pressure, detected over hours or days as the liquid slowly vents to space. By the time flight controllers realize a leak has started, significant coolant may already be lost. For a crewed spacecraft, losing coolant is a race. The vehicle has to reach a safe thermal state before the crew overheats or before critical electronics start shutting down. Most crewed vehicles carry backup cooling loops and reserve coolant. Still, a major loss of thermal control on a long mission with no rescue possible, like a Mars transit, would be a mission-ending event. The crew might not die from the thermal failure directly, but the cascading loss of computer cooling, of life support cooling, of power generation cooling would take down the vehicle's systems one by one. The Space Shuttle program studied this problem obsessively. A shuttle orbiter's Freon radiators were known to be vulnerable. Engineers estimated that any mission longer than about 30 days would face unacceptable risk of a mission-ending radiator impact, simply from cumulative exposure time. The shuttle was never designed for long missions, but the limit was effectively locked in by the radiator hardware. If you wanted to stay up longer, you needed better protected radiators, and the shuttle did not have room for the mass. Micrometeoroid armor, in the form of bumper shields placed ahead of critical surfaces, helps. The impact plasma from a hit on the bumper spreads out before reaching the real hardware, reducing the local damage. Station modules use this approach for their pressure hulls, but every bumper adds mass. Every pound of mass is a pound of propellant not carried. Every pound of propellant not carried is a day of mission time that cannot be flown. Deep space probes like Voyager carry no coolant loops at all. They use radioisotope power, which generates waste heat by its own physics, and they shed that heat through passive radiators fixed directly to their structure. Those radiators can take impact damage without losing fluid, because there is no fluid. The cost is that deep space probes cannot reject as much heat as active systems could. Voyager's total waste heat load is in the hundreds of watts, not the tens of thousands. Anything on a crude scale needs active cooling, and active cooling means coolant, and coolant means vulnerability. In November of 1914, a Soviet chamber technician was about to find out how fast vacuum exposure can turn a routine test into a horror story. December 1965, Houston. A vacuum chamber at what was then called the Manned Spacecraft Center sat with the pressure pulled down toward the vacuum of space. Inside the chamber, a technician named Jim LeBlanc was wearing a prototype Apollo spacesuit, testing whether the suit could hold pressure against simulated space conditions. LeBlanc was strapped in and breathing from the suit's internal oxygen supply. The chamber was at roughly 150,000 feet equivalent altitude, which is close enough to vacuum that the human body treats it the same way. A hose running into the suit kept it pressurized. As long as the hose held, LeBlanc was fine. The hose disconnected. It was a simple mechanical failure. A fitting that was supposed to stay locked came apart. Oxygen began venting out of LeBlanc's suit into the near vacuum around him, and the internal pressure of the suit started dropping toward the ambient pressure of the chamber, from 1 atmosphere down towards 0 in seconds. LeBlanc was conscious for what happened next, and he has described it in interviews since. He felt the saliva on his tongue start to bubble. The low pressure was pulling the dissolved gases out of the water in his mouth, and it was happening fast enough that he could feel it as a tingle across his tongue. In the seconds after that, he lost consciousness. Full vacuum exposure does not give a person time to do much more than notice it is happening. The chamber technicians saw the failure immediately. Repressurization procedures started within seconds. The chamber had to be brought back up to breathable pressure carefully, because a too fast repressurization could cause its own medical problems, but the team had drilled for exactly this situation. By the time LeBlanc was pulled out of the chamber, roughly 30 seconds of exposure had passed. He came around with the chamber still repressurizing and was able to describe what he had felt. The accident established several things about vacuum exposure that engineers and physicians had theorized, but never actually observed in a human subject. First, the body did not freeze. LeBlanc was in a vacuum environment for half a minute, with only his suit's insulation between him and the chamber walls, and his core temperature barely moved. Radiation is too slow. In the timescales that matter for vacuum exposure, thermal transfer to a human body is a non-factor. The cold of the vacuum chamber, even drawn down to simulated space conditions, was nothing compared to the oxygen deprivation that would have killed him in another minute or two. Second, the tongue bubble effect is real. At low enough pressures, water boils at body temperature, not because the water is hot, but because the pressure is low enough that the liquid state is no longer stable. Any exposed moist tissue, the tongue, the eyes, the mucous membranes, will start to boil. Skin does not, because skin is dry, and the underlying tissues are held at internal body pressure by the skin itself, but a mouth open to vacuum will bubble. Third, useful consciousness lasts about 10 to 15 seconds in full vacuum exposure. LeBlanc stayed awake long enough to register the failure and understand it was happening before his brain ran out of oxygen. Any emergency response has to happen within that window. The accident changed Apollo suit design. Hose fittings got better locks. Suits got faster-acting emergency oxygen reservoirs. Test protocols changed so that no technician was ever in the chamber alone, and repressurization teams were always on standby. LeBlanc recovered fully, went back to work, and continued testing suits for the rest of the Apollo program. The man who briefly went into vacuum and came back out lived into his 80s. The deeper lesson was medical. The body does not freeze, the body does not explode, the body runs out of air. And the specific way it does that is worth understanding, because it drives the design of every emergency system on every crewed spacecraft flying today. The moment pressure drops to near zero around a human body, a cascade of effects begins. Understanding the sequence matters, because it tells you what an emergency response team actually has time to do, and what they absolutely do not. At the first second of exposure, the dissolved gases in the blood and tissues start coming out of solution. Nitrogen, which makes up most of what is dissolved in human blood, forms bubbles inside blood vessels. Physicians call this ebulism, and it is the same phenomenon that kills deep-sea divers who surface too fast. The difference is that in a vacuum, it happens everywhere in the body at once, not just in the joints. At around 3 seconds, the lungs become a liability. If the person has their mouth closed and is holding breath, the pressure difference between the lungs and the near vacuum outside becomes dangerous. The lungs are built to hold gas at 1 atmosphere. Exposed to vacuum, that atmosphere of pressure is pushing outward against tissues that cannot contain it. The trained response drilled into every astronaut is to exhale immediately on decompression. Do not hold your breath. Let the air out. A held breath can rupture lung tissue. By about 5 seconds, the tongue and eyes begin boiling at body temperature. The moist surfaces start producing vapor. The eyes swell slightly. The tongue fizzes. Saliva turns to mist. By 10 seconds, circulation is failing. The blood the heart is trying to pump is now full of gas bubbles, and bubbly blood cannot carry oxygen efficiently. Brain oxygen levels start dropping fast. By 15 seconds, the person loses consciousness. This is the hard edge of useful exposure time. A person in full vacuum who is still awake at the 15-second mark is statistical noise. Almost everyone is out by then. From 15 seconds to about 90 seconds, the body continues to exist but is no longer fighting. The heart keeps beating for a while. The tissues slowly expand as more dissolved gas forms bubbles, giving exposed skin a swollen appearance that some accounts describe as looking like a bodybuilder rather than an overfilled balloon. Skin never ruptures. The human body is strong enough to hold itself together against 1 atmosphere of internal pressure. The swelling is noticeable, but not catastrophic. After about 90 seconds, the damage starts to be permanent. Brain tissue without oxygen for that long begins to die. Heart muscle, deprived of oxygenated blood, loses the ability to contract properly. Resuscitation becomes difficult and past 2 minutes, essentially impossible. Note what is not on this list: freezing, explosion, instant death. None of those things happen. Vacuum kills by asphyxiation, with embolism as an aggravating factor. It is a quieter killer than the movies portray, and in some ways a more insidious one, because a person exposed to vacuum looks mostly fine for the first few seconds. They are still breathing out, still conscious, still capable of trying to grab a rescue line or pull themselves toward an airlock. The window for self-rescue is real, and astronauts train for it. This is the physiological reality behind every design decision on a crewed spacecraft. Pressure suits are rated to hold breathable atmosphere against the vacuum for specific durations. Emergency oxygen bottles carry minutes, not hours, of supply because minutes are all anybody has. Airlock designs emphasize fast repressurization, so a crew member with a damaged suit can be brought to survivable conditions quickly. The cold of space in all of this is almost an afterthought. It is real. It is deep. It would eventually freeze a body solid. But it is slow. Humans in vacuum die of other things first, and the engineering that keeps them alive is almost entirely focused on pressure and oxygen, not temperature. Temperature matters for the spacecraft. For the human, the killers are faster. Now back inside the ship, the machines that keep every crew alive are built around one quiet piece of hardware that you've probably never heard of, but that runs through every mission like circulatory plumbing. A heat pipe is a sealed tube, usually made of copper or aluminum, partially filled with a working fluid. It has no moving parts. It uses no electrical power. It is sometimes as small as a pencil, sometimes as long as a row of lockers, and it moves heat faster than any solid material known to engineering. The principle is elegant. The tube is sealed in vacuum except for a small amount of fluid inside, usually water or ammonia for terrestrial applications, methanol or other specialized liquids for spacecraft. The fluid sits at a temperature where it boils easily. One end of the tube is mounted against a heat source, the other end is mounted against a heat sink. As heat flows into the first end, it boils the fluid there. The resulting vapor rushes through the interior of the tube toward the cold end because vapor pressure is higher where the fluid is boiling. At the cold end, the vapor condenses back to liquid, releasing its heat of vaporization into the sink. The condensed liquid then flows back along the inside wall of the tube, either by gravity or by a wick structure that draws it by capillary action, returning to the hot end to boil again. A loop, continuously running, driven by nothing but temperature differences and the phase change of the fluid. The reason this matters so much in space is efficiency. A copper rod moves heat by conduction, and conduction in a solid is limited by the thermal conductivity of the material. Copper is one of the best conductors available, but a heat pipe filled with water moves heat hundreds of times more effectively than solid copper of the same dimensions. The phase change of the fluid is what does it. Vaporization absorbs enormous energy. Condensation releases enormous energy. Moving the heat as vapor is vastly more efficient than moving it as hot metal. Spacecraft use heat pipes everywhere, behind electronics racks to spread heat from hot chips to cooler structural panels, along the length of radiator panels to distribute heat evenly across the panel surface so the whole panel radiates at once instead of a hotspot trying to dump everything through a small area. Inside instruments, to move heat from sensitive detectors to external radiators. On interplanetary probes, to carry heat from radioisotope power sources to where it is useful or where it can be dumped. The Mars rovers use heat pipes to move waste heat from their plutonium power sources into the rover body overnight, keeping the electronics warm enough to survive the Martian night. The same heat pipes then reverse direction during the Martian day when the rover is working hard and overheating, shedding the heat out to external radiators. A single piece of hardware, doing opposite jobs at different times, with no moving parts and no power consumption. Heat pipes have limits. They only work if the hot end is actually hotter than the cold end. If both ends sit at the same temperature, the fluid stops cycling and the pipe becomes just a sealed tube of liquid. This is why heat pipes on deep space probes have to be carefully oriented and thermally coupled to ensure the temperature gradient never reverses during the mission. A pipe that accidentally pipes heat backward from a hot radiator into a cold instrument is a disaster. The International Space Station uses variants called capillary pumped loops for some of its internal cooling, essentially heat pipes with more sophisticated wick designs that can handle larger heat loads and longer distances. Modern spacecraft cooling design is largely the art of picking the right variant of the heat pipe for each application, wiring them together, and letting physics do the rest. The downside is that heat pipes only move heat. They do not get rid of it. A heat pipe takes waste energy from one place and delivers it to another, and at the end of the line, something still has to radiate that energy into space. For the final stage of the cooling chain, the spacecraft wraps itself in one of the thinnest, shiniest, most important materials in orbital engineering. Every spacecraft you've ever seen in a photograph has that crinkly gold or silver wrap covering most of its surface. It looks like someone tried to shrink wrap a sculpture in kitchen foil. That material is multi-layer insulation, and it is doing one of the most important jobs on the vehicle. A single sheet of aluminized plastic film is a poor insulator on its own. Stack 15 or 20 of them with gaps between each layer, and the stack becomes one of the best thermal barriers known to engineering. Each sheet reflects the vast majority of infrared radiation that tries to cross it. A photon of thermal radiation leaving a hot surface hits the first layer, mostly bounces back. Some gets through. The small fraction that passes then has to bounce off the second layer, which reflects most of it again. By the time radiation has worked its way through 20 layers, only a tiny fraction of the original heat has made it across. The layers never touch each other. If they did, heat would conduct through the contact points and bypass the whole reflective trick. Tiny separator materials, usually a mesh of silk or polyester, hold the layers apart while adding almost no thermal bridge. The whole stack is light, flexible, and can be shaped around almost any spacecraft geometry. Multi-layer insulation, or MLI, is the reason spacecraft skin temperatures can be controlled at all. Without it, the hot side of a vehicle in direct sunlight would conduct heat through the hull and into the crew cabin. The cold side would bleed heat out through the hull and chill the cabin. The interior would be a swinging temperature roller coaster with every orbit or attitude change. With MLI, the external hull thermally isolates from the interior. The outside of the insulation can swing through enormous temperature ranges while the inside barely moves. The interior temperature gets determined by the active thermal control system, the fluid loops and heat exchangers and radiators. The blanket just blocks the outside environment from interfering. Different parts of a spacecraft use different MLI configurations. A crew module might have 20 or 25 layers because keeping crew comfortable is a high-stakes problem. A propellant tank that needs to stay cold might use a heavier MLI stack, with extra reflective coatings to minimize heat input from the hull. A radiator panel, by contrast, uses almost no MLA on its outward-facing side because the whole point of the panel is to radiate heat. The MLI is only on the back of the panel, to prevent it from picking up warmth from the spacecraft behind it. The material has its own vulnerabilities. MLI is thin and delicate. Micrometeoroids punch through it easily, although the damage is usually cosmetic because the layers are redundant, and a few holes do not significantly hurt the overall performance. Ultraviolet radiation degrades the plastic substrate over years in orbit, gradually darkening the material and making it less reflective. Long-duration missions plan for this degradation, sizing their insulation thicker than minimum requirements to give margin for aging. One specific failure mode matters. MLI blankets can develop gaps at seams and penetrations. Every place a cable exits the insulation, every bracket that pokes through, every mounting point becomes a local thermal short circuit. Detailed thermal models of a spacecraft treat every penetration individually, calculating the heat leak through each one, and making sure the total adds up to something manageable. Experienced engineers sometimes say that MLI is only as good as its worst seam. The material is also what makes distant probes survive in the cold. A Voyager spacecraft 40+ years into interstellar space is wrapped in MLE that traps the heat from its plutonium power source long enough for the electronics to function. Without that insulation, the cold of deep space would steal the heat away faster than the radioisotope generator could produce it, and the probe would freeze even while its power source was still running. The cold of space is relentless, but the cold of a planetary surface without an atmosphere is worse because it lasts 14 days. The moon rotates on its axis once every 29.5 Earth days. This means any spot on the lunar surface experiences about 2 weeks of continuous daylight followed by about 2 weeks of continuous night. There is no atmosphere to smooth the transition. When sunset comes, surface temperatures plunge from around 250 degrees Fahrenheit to roughly 250 below. The drop happens over hours, and then the cold just stays there for 350-some consecutive hours. Any hardware left on the lunar surface has to survive that cold. Most cannot, and they die. The Chinese Chang'e missions have been the most public example. Chang'e 3, which landed in 2013, and its rover U2 carried radioactive heat sources to keep critical components warm during the lunar night. The rover would drive during the lunar day, then park itself in a specific orientation with solar panels folded over sensitive electronics to provide insulation and essentially hibernate for 2 weeks. A small amount of radioactive decay heat, supplemented by stored energy, kept the electronics above the minimum survival temperature of roughly -70 degrees Fahrenheit. Most electronic components stop working below about -40 degrees. Batteries freeze, lubricants seize, circuit boards crack from thermal contraction. To keep a rover alive through lunar night, every vulnerable subsystem needs either a heater or a temperature-tolerant design. The heaters need power, the power needs batteries, the batteries themselves need to be kept warm enough to hold charge, and 14 days of night means 14 days of no solar recharging. Every watt of heating has to come from stored energy or from a radioactive source. The Apollo surface missions did not face this problem directly. Every Apollo landing was timed to occur during lunar morning, when the sun angle was low enough to cast long shadows that helped the crew navigate, and when surface temperatures were manageable. No Apollo mission stayed on the surface for more than about 3 Earth days, so the crews were always long gone before sunset approached. The lunar module itself had to survive through subsequent lunar nights as abandoned hardware, but by then no one was using it. Any long-duration lunar mission has to solve the night problem. Proposed lunar bases have relied on nuclear power sources, specifically small fission reactors, because photovoltaics alone cannot carry the base through 2 weeks of darkness. The Kilopower project, tested on the ground by NASA in 2017 and 2018, demonstrated a small nuclear reactor that could provide about 10 kilowatts of electrical power continuously, enough to keep a small habitat warm and pressurized through any duration of darkness. Scaled-up versions of that technology, now being developed under the Fission Surface Power Program, aim to deliver 40 kilowatts or more, enough to support meaningful habitation. The other strategy is geography. Near the lunar poles, certain crater rims stay in nearly continuous sunlight, because the sun grazes the horizon at a very shallow angle for months at a time. A solar array mounted on a high tower at one of these peaks can receive sunlight for the vast majority of the lunar year. This is why the Artemis program has targeted the south pole of the moon for its planned landings. The peaks of eternal light, as those locations are called, offer something no other place on the lunar surface can provide: reliable solar power. Even at the poles, shadowed craters exist. Some craters near the poles have interiors that have not seen sunlight for billions of years. The temperatures inside those craters can drop below -400 degrees Fahrenheit, colder than most of the outer solar system. Ice deposited by ancient comet impacts sits frozen on the crater floors, preserved by the permanent shadow. Those same locations as targets for future water ice mining, but any mission going into them has to bring its own heat. A rover entering a permanently shadowed crater is going into conditions colder than Pluto. Its entire thermal design has to be reimagined for that environment, and when a lander got this kind of calculation wrong, the result was a spacecraft frozen to death on a comet. The European Space Agency's Philae lander separated from the Rosetta spacecraft on November 12, 2014, and drifted down toward the surface of Comet 67 P. Churyumov-Gerasimenko. It was the first time any human-built craft had attempted a soft landing on a cometary nucleus. The engineering problem was staggering. The comet was a lumpy, irregular ball of ice and dust about 2.5 miles across with almost no gravity. A person standing on its surface could jump and reach escape velocity. Philae had to land softly enough to stay put on that surface, without being able to rely on gravity to hold it down. The design used harpoons and screws. When Philae contacted the surface, harpoons were supposed to fire into the ice to anchor it, and ice screws on its 3 feet were supposed to drill in and lock it down. None of it worked as planned. The harpoons never fired. The thruster that was supposed to push Philae down onto the surface during landing did not activate. When the lander touched the comet, it bounced. In the nearly zero gravity of the comet, the bounce carried Philae about a kilometre back up off the surface, and it drifted for almost 2 hours before coming down again. It bounced a second time. Finally, on its third contact, it came to rest. The rest point was nowhere near the planned landing site. Philae ended up wedged against a cliff face, tilted at an angle, with 2 of its 3 feet on the ground and 1 in the air. The location turned out to be an almost permanent shadow. The comet's surface features blocked sunlight from reaching Philae's solar panels for all but about 90 minutes of each 12-hour cometary day. Philae had been designed with a primary battery that could run its instruments for about 60 hours after landing, and secondary rechargeable batteries that were supposed to be topped up by the solar panels to extend the mission. The plan was for Philae to use its primary battery to run initial science operations, then shift to solar-powered operation for a much longer mission duration. In the shadow where Philae actually landed, the solar panels could not recharge the batteries. The lander had 60 hours of power and no way to get more. The team on Earth worked frantically to execute as many science operations as possible in those 60 hours. Instruments collected data. Drills sampled the comet's surface. Cameras imaged the environment, and then the primary battery ran down. Philae went silent on November 15th, about 60 hours after landing. The lander was not destroyed. It was just cold. Its electronics had gone into a safe mode as temperatures dropped, and without sunlight to recharge the batteries, it could not bring itself back online. Months later, as the comet travelled closer to the star and the local sun angle changed, Philae's solar panels briefly received enough sunlight to wake up. The lander phoned home in June of 2015, transmitted some telemetry, and then fell silent again as the geometry shifted. It was heard from a few more times over the following weeks, in short bursts, and then nothing. Rosetta eventually imaged Philae's resting place from orbit. The lander was exactly where telemetry had suggested, wedged against a cliff, tilted in shadow. The mission recovered an enormous amount of science data. Philae had done most of what it was designed to do in those first 60 hours, but the shadow was what killed it, not the bounce, not the harpoon failure. A slightly different landing point, a few hundred feet in a better direction, and the lander would have had sunlight for years. For any crewed mission going to a planetary surface, this is a cautionary tale. Sunlight is power. Power is heat. Lose either one for long enough and the spacecraft goes cold, and cold spacecraft do not come back. SpaceX is about to find out how true that is on a much bigger scale. Starship is the largest spacecraft ever built. The fully stacked vehicle stands almost 400 feet tall, weighs about 5,000 tons fueled, and is designed to eventually carry up to 100 people at a time to the surface of Mars. Elon Musk has publicly targeted crewed Mars landings within the decade, though the timeline has slipped repeatedly since the vehicle's original concept was announced. There are many engineering problems with sending Starship to Mars. The one that mission planners keep quietly asking about is how the vehicle will keep its crew cool during a 6 to 9 month interplanetary coast. A crewed Starship carrying 100 people would generate enormous waste heat. 100 humans at rest put out 10,000 watts of metabolic heat alone. Add life support systems scaled to support that many people, electronics, experiments, food preparation, and lighting, and the waste heat load climbs well above 50,000 watts. In sustained operation, possibly over 100,000 watts. The vehicle has limited external surface area for radiators. Its stainless steel hull is roughly 9 meters in diameter and about 50 meters long. Wrapped fully, That gives maybe 3,000 square feet of external skin, but most of it cannot be used as a radiator. The engines take up one end. The nose cone is aerodynamically shaped for atmospheric re-entry. The sides get hot from solar heating during part of the coast. Practically useful radiator area is maybe a quarter of the total hull. SpaceX has not publicly disclosed the thermal control architecture for a crewed Mars Starship. Public talks and interviews have focused on the propulsion and life support systems, but the radiator question rarely comes up. Industry observers with experience in thermal engineering have raised concerns about whether the Starship design, as currently shown, has enough radiating surface to support the stated crew capacity for the duration of a Mars transit. Several possibilities exist. The vehicle could deploy external radiator panels during coast, stored inside during launch and landing. Such panels would need to unfold from a compact launch configuration to a large operating configuration, survive the vibration and acceleration of launch, and refold before Mars landing to avoid interfering with atmospheric entry. No spacecraft of this scale has ever attempted such a deployment. Another possibility is that the crew size for early Mars transits will be much smaller than 100, and the waste heat load will scale down accordingly. Early missions might carry 10 or 20 people, rather than the full headline capacity. At that scale, the thermal problem becomes manageable with the available hull surface, assuming careful attention to which parts of the hull are kept pointed at cold space during coast. A third possibility is active cooling using consumable water. The vehicle carries water for crew use and for life support regeneration, and water can be used as an emergency heat sink by boiling it off to space. This works in the short term but consumes water that the crew needs for other purposes. Over a 9-month transit, water consumption for thermal control could become a significant fraction of the total water budget. The real answer is probably some combination: deployable radiators for steady-state heat rejection, consumables as emergency capacity, and careful attitude control to keep solar loading minimized during the coast. The engineering choices will define what a crewed Starship actually looks like once it flies with people, and those choices have not yet been publicly finalized. On the Martian surface, the problem becomes different, but equally hard. Mars has an atmosphere, thin but present, and a day-night cycle that delivers both heating and cooling over a 24.5-hour period. A habitat on Mars generates waste heat that has to leave the habitat one way or another. Some of it can radiate to the Martian sky, which is cold enough to serve as a heat sink during the night. Some of it can be dumped into the regolith through buried heat exchangers. Some can be rejected through convective cooling to the thin Martian atmosphere. All of these systems need power, and the power source on Mars for any meaningful habitation is almost certainly going to be nuclear. Solar panels on Mars do a mediocre job. The planet receives about 43% of the solar intensity that Earth gets, simply because Mars is farther from the star. The atmosphere, thin as it is dusty enough that dust storms can reduce the amount of sunlight reaching the ground by 90% or more during bad episodes. Some storms cover the entire planet for weeks at a time. Any Mars surface mission relying on solar power has to size its arrays and batteries for worst-case dust events, which pushes the hardware requirements up dramatically. The alternative is nuclear, specifically fission reactors. NASA's Fission Surface Power Project is developing small nuclear reactors for use on the Moon and Mars. The current target is a 40-kilowatt electric system that can run continuously for at least 10 years without refueling. Multiple reactors would be deployed together to provide the total power a crewed habitat needs, with redundancy in case one unit fails. The reactors themselves would be relatively compact, about the size of a large refrigerator. They use highly enriched uranium fuel, a moderator to slow neutrons for efficient fission, and a heat exchanger to transfer reactor heat to a power conversion system. The power conversion system, probably a Stirling engine or a Brayton cycle turbine, turns heat into electricity. And here is where the thermal problem slams in. A Stirling engine at realistic space conditions runs at maybe 30% efficiency. That means for every kilowatt of electricity the reactor produces, roughly 2 to 3 kilowatts of waste heat has to be dumped. A 40 kilowatt electric reactor is rejecting something like 80 to 120 kilowatts of thermal waste into the environment, continuously for 10 years. On Mars, with a thin atmosphere, some of this heat can be dumped by convection to the air and by conduction to the regolith. But the bulk has to go through radiators, big ones. The reactor design includes radiator panels that unfold from the launch configuration into a much larger deployed geometry, probably hundreds of square feet per reactor unit. Those panels need to survive Martian dust storms, thermal cycling between cold nights and warmer days, and the occasional impact of windblown grit. The reactors also need to be placed far enough from the crew habitat that their radiation does not endanger the astronauts. Current concepts put reactors a mile or more from the crew living area, with the reactor sitting in a shallow excavation or behind a natural terrain feature that blocks direct radiation. Power is then carried to the habitat through buried cables. The habitat itself has its own thermal balance to manage. Mars is cold. Nighttime temperatures at mid-latitudes can drop to minus 130 degrees Fahrenheit. The habitat has to be heated to keep the crew comfortable and to prevent water in the life support system from freezing. The reactor provides plenty of electricity for heaters, but the heaters add to the habitat's internal heat load, which then has to be balanced against losses through the habitat walls to the cold environment outside. On the coldest nights, the habitat is a small oasis of warmth bleeding heat into the Martian atmosphere faster than the crew can generate it. The reactor has to keep up. On the warmest days during summer at low latitudes, solar heating of the habitat plus crew metabolism plus electronics could push the habitat toward overheating, and radiators have to dump the excess. The reactor power system, the habitat thermal control system, and the life support system are all interacting constantly. A failure in any one could cascade into a failure of the others. Mars mission design has to account for all of this, and the designs have been iterated for decades without a flight-ready vehicle yet emerging. A lower-tech approach has been carrying spacecraft since the 1960s, and it is still keeping the most distant human-made objects alive. The two Voyager probes launched in 1977 on missions intended to last a few years. They are both still operating more than 48 years later, at distances well beyond the orbit of Pluto. Voyager 1 is currently over 15 billion miles from the star, the farthest human-made object ever. Voyager 2 is not far behind. At those distances, sunlight is essentially useless as a power source. The star appears as just another bright point in the sky, delivering roughly 1,000 times less energy per square foot than it does at Earth. Solar panels cannot work. Nuclear power, specifically radioisotope thermoelectric generators, is the only option that makes sense. Each Voyager carries 3 radioisotope thermoelectric generators, called RTGs. An RTG is essentially a chunk of plutonium-238, wrapped in a structure that converts some of the decay heat into electricity. Plutonium-238 decays by emitting alpha particles, and that decay produces a steady output of heat. Thermoelectric couples around the plutonium use the temperature difference between the hot plutonium and the cold external radiator to generate electric current. No moving parts, no fuel to run out of, at least not on any human timescale. When Voyager 1 launched, its RTGs produced about 470 watts of electric power combined. Today, after nearly 5 decades, they produce about 225 watts. The plutonium is slowly decaying, the thermoelectric materials are slowly degrading, and the output is dropping by about 4 watts per year. At this rate, the probe will lose enough power to run its remaining instruments sometime in the late 2020s. The operations team has been shutting down instruments one by one over the past decade to stretch the remaining power as far as possible. What is less widely discussed is that the RTGs are also the probe's heaters. The same plutonium that generates electricity also produces far more waste heat than the electrical output alone represents. An RTG producing 200 watts of electricity is also dumping something like 2,000 watts of waste heat, most of which would be lost to space if it were not captured. Voyager's engineers captured it. The spacecraft has an intricate thermal design that routes RTG waste heat through the body of the probe to keep the electronics warm. Plumbing is not the right word because there are no fluid loops, conduction paths, small heat pipes, radioisotope heater units specifically, small packets of plutonium that generate only a watt or so of heat each, scattered throughout the spacecraft to keep individual components above their minimum operating temperatures. Without those heaters, Voyager's electronics would freeze below their operating limits within days. Deep space is cold enough that even a nuclear-powered spacecraft has to aggressively capture and redistribute its own waste heat to stay functional. The plutonium is not just power, it is survival. This is why Voyager is still running after nearly half a century. The decision to use a nuclear power source, made in the 1970s, was not just about providing electricity, it was about providing a continuous trickle of heat that could keep the spacecraft alive in an environment where sunlight was essentially absent and temperature was the primary threat. Modern deep space probes follow the same model. New Horizons, the probe that flew past Pluto in 2015 and is now heading into the Kuiper Belt, carries a single RTG. Cassini, which orbited Saturn from 2004 until 2017, carried 3. Perseverance, the latest Mars rover, carries a smaller version designed for surface operations. Every one of these missions chose nuclear power because solar does not work far from the star, and battery-only operations do not last long enough to justify the mission. And as we move out from the inner solar system, the cold gets worse in a way that catches even experienced engineers by surprise. The interstellar medium, the space between the stars, is not empty in the strict sense. It contains a few atoms per cubic yard, mostly hydrogen, some helium, a trace of heavier elements. That is an absurdly thin gas by any earthly standard. It is roughly 1 trillion times less dense than the air at Earth's surface. The pressure in interstellar space is so low that calling it a gas feels like a misuse of language. For a spacecraft travelling through this region, the few atoms that exist matter less than what is not there. What is not there is starlight of useful intensity. In the outer solar system, beyond the orbit of Neptune, solar intensity drops to less than 1,000th of its value at Earth. By the time a probe crosses into true interstellar space, the star is just another dim point. There is no source of external heat to keep a spacecraft warm. Whatever warmth exists has to come from inside. The thermal problem shifts. In the inner solar system, the struggle is to reject waste heat. In the outer solar system and beyond, the struggle is often to keep enough heat to survive. A probe that was designed with big radiators to dump heat near Earth might find itself losing heat faster than it can generate it when it reaches the outer planets. This is why Voyager probes run plutonium heaters and carefully managed insulation. It is why Cassini used its own waste heat as carefully as any survival shelter. It is why any future interstellar probe will need to carry a substantial heat source just to keep its electronics functional during the decades or centuries of the journey. A proposed mission called Interstellar Probe, currently in study phase at Johns Hopkins Applied Physics Laboratory, would aim to reach about 50 billion miles from the star, significantly farther than Voyager. The mission concept calls for a nuclear power source similar to those used on Cassini and Voyager, sized to provide about 300 watts of electrical power and roughly 10 times that amount of thermal waste heat. The thermal waste heat is not a byproduct to be discarded. It is an essential feature, keeping the spacecraft warm enough to function at temperatures that would otherwise drop toward the ambient of interstellar space. Over long time scales, the thermal situation becomes tighter. A probe that takes a century to reach a nearby star is looking at a 100-year mission, and its nuclear power source has to last that long. Plutonium-238 has a half-life of about 88 years, which means after a century the power output has dropped to less than half of its launch value. Heater output drops at the same rate. The spacecraft has to be designed to still function with half the thermal budget it started with, and the calculation is not forgiving. A truly ambitious interstellar mission, one aiming at Alpha Centauri 4 light-years away, would face a journey of decades at best, centuries at worst. Breakthrough Starshot, a concept for tiny probes pushed by ground-based lasers to a significant fraction of light speed, would make the trip in about 20 years. The probes themselves would be gram-scale, too small to carry nuclear power, and they would essentially freeze to deep space ambient during their long coast. They would wake up briefly on arrival, use whatever stored charge they had to transmit a few data packets, and die soon after. Larger interstellar probes, the kind that could carry meaningful instruments, would need their own substantial heat sources, nuclear probably. And they would face the cold as an active adversary throughout the mission, not a passive backdrop. Closer to home, a mission to Jupiter faces its own thermal nightmare when it tries to carry a crew. Crewed missions to Jupiter have been studied repeatedly over the decades, usually as the next logical step after Mars. The distance is vast. Jupiter is more than 5 times farther from the star than Earth, and a crewed mission would take years round trip. The radiation environment around Jupiter is extreme, dominated by the planet's magnetosphere, which accelerates charged particles to lethal energies. Any crewed spacecraft operating near Jupiter needs serious shielding just to keep the crew alive during the encounter. The shielding adds mass. The added mass needs more propulsion. The propulsion generates more waste heat. The waste heat needs more radiators. And at Jupiter's distance, the lower solar intensity means solar panels are about 25 times less effective than they would be at Earth, which pushes nuclear power from preferred to mandatory. A realistic crewed Jupiter mission architecture looks something like this. A large interplanetary transfer vehicle carrying the crew and their supplies, powered by either nuclear electric propulsion or a nuclear thermal rocket. Both options involve reactors producing megawatts of thermal power, of which only a fraction becomes useful propulsive energy. The rest is waste heat that has to be radiated away. A nuclear electric vehicle operating at 1 megawatt of reactor output and a 30% conversion efficiency is rejecting about 700 kilowatts of waste heat continuously during its thrust phase. At a radiator temperature of 600 Fahrenheit, the required panel area is something like 2,000 to 3,000 square feet. That is a football field of radiating surface on a single vehicle, stretched out in whatever geometry the engineers can make work. The radiators have to point edge-on to the star to minimize solar heating. Jupiter's distance helps with this because solar intensity is already low, but the radiators still cannot afford to be sunlit during operation. The vehicle has to be designed so that the radiator panels deploy in a plane perpendicular to the sun line, rotating slowly as the vehicle travels to keep the correct orientation. The structural challenge is severe. Football field-sized panels unfolding from a compact launch configuration, surviving years of thermal cycling as the vehicle accelerates and decelerates and changes orientation. Any mechanism that drives those panels has to be reliable for the entire mission duration. A jam in a deployment joint 2 years out from Earth is an unrecoverable failure. The mass budget gets ugly fast. A full-scale Crude Jupiter mission vehicle carrying its own radiators, reactor, shielding and consumables for a multi-year journey weighs in at several hundred tons in orbit. Getting that mass to orbit requires multiple heavy lift launches and on-orbit assembly, probably spread over years. The full stack has never been built. The closest things to it are the various nuclear thermal and nuclear electric studies that NASA and industry have published over the decades, and each one has ended with the same conclusion. The vehicle is possible in principle, but the cost and complexity are enormous, and the thermal control system is one of the biggest drivers. Thermal engineers who have worked these studies tend to hold the same view. The radiators are not a detail, they are the ship. A Crude Jupiter vehicle is primarily a giant radiator array with some incidental pressurized modules attached for the crew, and before any crewed spacecraft can even reach Jupiter, it has a simpler thermal problem to solve on the way, keeping its fuel from evaporating. Liquid hydrogen is the best rocket fuel humans know. It has the highest specific impulse of any chemical propellant, meaning it delivers the most thrust per pound of fuel burned. Every serious interplanetary mission architecture uses hydrogen for at least some of its propulsion stages, because the alternative chemistries give up too much performance to be competitive. Liquid hydrogen boils at roughly minus 423 degrees Fahrenheit. It has to be kept below that temperature, or it turns back into gas and rushes out of whatever tank is holding it. The colder it stays, the less is lost. The warmer it gets, the faster the losses. In space, hydrogen tanks face a thermal environment that constantly tries to warm them. Solar heating on the sunlit side of the tank, infrared emission from nearby spacecraft structure, heat leaks through the tank supports and plumbing. Every one of these sources contributes to boiloff, the slow conversion of liquid hydrogen to gaseous hydrogen that has to be vented overboard to prevent pressure from building up. A typical launch vehicle upper stage with liquid hydrogen can tolerate boil-off rates of a few % per day, because the stage only needs to store hydrogen for hours before it fires its engines and burns the fuel. But a mission that requires hydrogen to remain liquid for weeks or months, like a Mars mission using hydrogen for Trans-Mars injection after a long orbital loiter, faces much tighter constraints. Boil-off rates need to drop below about 1% per month to keep the propellant mass from draining away before the mission needs it. The solutions are variants of the same techniques used for cryogenic instrument cooling. Multi-layer insulation wrapped around the tanks, typically much thicker stacks than used for other spacecraft surfaces. Shields that block infrared radiation from nearby structure, sunshades that keep the tanks in permanent shadow during orbital coast, active cooling systems using small cryocoolers to pull heat back out of the tank when boil-off starts. NASA's Glenn Research Center has been developing active zero boil-off technology for years. The concept uses cryocoolers similar to those used on Webb, plumbed directly into the hydrogen tanks to actively refrigerate the propellant rather than just insulate it. A sufficiently capable cryocooler can hold a tank at its target temperature indefinitely, with boil-off effectively zeroed out. The cost is electrical power to run the cooler, which on a long mission can be substantial but is much less than the mass of propellant that would otherwise boil away. The technology has been tested on the ground and in limited flight demonstrations. It has not yet been used on a flagship mission. The next big test will probably come with Artemis missions that use hydrogen, oxygen upper stages for lunar departure, where multi-day storage is required and boil-off has to be managed actively. For Mars missions, the problem becomes worse. A crewed Mars mission might need to store liquid hydrogen in Earth orbit for weeks before departure, then in transit for months, and potentially at Mars itself for the entire surface stay before the return trip. Total storage time approaches 2 to 3 years. Without active cooling, the propellant mass lost to boil-off would double or triple the required launch mass from Earth. With active cooling, the numbers start to close. Every proposed crewed Mars architecture from the 2010s onward has assumed zero boil-off propellant storage as a baseline technology. None of them have demonstrated it yet at the scale required. The technology gap between tested on the ground and reliable for a crewed mission remains one of the quieter but more important hold-ups for serious interplanetary flight. The cold that is a tool for keeping fuel liquid is the same cold that, elsewhere in the universe, produces phenomena so extreme that they defy our best theories. About 5,000 light-years away, in the direction of the constellation Centaurus, a dying star has created the coldest known place in the natural universe. Astronomers call the object the Boomerang Nebula, because early images showed a vaguely boomerang-shaped cloud of gas. Later, higher resolution images revealed a more bow-tie-like structure, with lobes of gas expanding outward from a central star. The temperature inside the Boomerang Nebula is about 1 degree above absolute zero. That is colder than the cosmic microwave background. The background, the remnant glow of the Big Bang that fills every cubic centimetre of empty space in the universe, sits at 2.7 degrees above absolute zero. Everywhere in the universe, that is the floor. No object can passively cool below the background, because the background radiation itself is always incoming, warming anything cooler than it. The Boomerang Nebula breaks this rule. The mechanism is rapid expansion. The central star at the heart of the nebula is in the late stages of its life, shedding its outer layers as a supergiant wind. The wind is blowing outward at roughly 370,000 miles per hour, which is fast even by stellar standards. As the gas expands, it does thermodynamic work against its own pressure, cooling in the process. This is the same principle that makes compressed air feel cold when you release it from a can. Expand a gas and it cools. In the Boomerang Nebula, the expansion is so rapid and the gas is so tenuous that the cooling happens faster than the microwave background can heat the gas back up. The gas drops below the background temperature and stays there, briefly, in a thermal state that should not exist according to the simple equilibrium arguments. The nebula is a natural refrigerator, running on stellar-scale expansion, producing temperatures that no other natural process is known to produce. Astronomers first noticed the anomaly in the 1990s, when observations of the nebula showed that it was absorbing the microwave background radiation rather than emitting it. Normally, any object in space is warmer than the background and emits infrared radiation that can be measured against the background's glow. The Boomerang was doing the opposite. It was appearing as a cold spot against the sky, absorbing microwave photons rather than emitting them. The only explanation that fit was that the nebula was colder than the background, which meant the expansion cooling was working on a scale no one had expected. The phenomenon is temporary. As the nebula continues to expand, the gas will eventually slow, and surrounding radiation will warm it back up toward background equilibrium. The current ultra-cold state probably only lasts for a few thousand years of the nebula's evolution. But for that window of time, the Boomerang represents a natural temperature that no other known object in the universe reaches. For engineers on Earth, the Boomerang is both a reminder and a challenge. A reminder that the universe can produce temperatures below the cosmic floor through physics that we understand but cannot replicate at scale. A challenge because nothing any human has ever built has stayed at such temperatures for more than fleeting experimental durations, except, interestingly, one experiment, and it is orbiting Earth right now. The Cold Atom Laboratory is a suitcase-sized experimental facility aboard the International Space Station. It has been operating since 2018. Its purpose is to produce Bose-Einstein condensates, a state of matter that exists only at temperatures extraordinarily close to absolute zero, and to study them in the microgravity environment of orbit. On Earth, Bose-Einstein condensates can be produced in ground-based laboratories, but they cannot be maintained for long. Gravity pulls the ultra-cold atoms apart. The condensate begins to fall under its own weight within milliseconds of being formed, and the experimental window is brief. In orbit, falling does not apply. A condensate floating in microgravity stays put, and the experimental window extends by orders of magnitude. The laboratory cools atoms using a sequence of laser traps and magnetic manipulations. Rubidium and potassium atoms are slowed by precisely tuned laser beams that push against them, robbing them of kinetic energy. Slower atoms are colder atoms in the strict physics sense. The slowest atoms are cooled further by evaporative cooling, where the hottest atoms are selectively allowed to escape a magnetic trap, leaving only the coldest atoms behind. After enough rounds of selection, the remaining atoms are at temperatures measured in billionths of a degree above absolute zero. In 2020, researchers at the Cold Atom Lab reported temperatures of roughly 100 picokelvin, about 100 billionths of a degree above absolute zero. That is vastly colder than the cosmic microwave background, vastly colder than the Boomerang Nebula, vastly colder than any natural process in the universe is known to produce, as far as current observations can tell. The temperature exists for a fraction of a second, in a volume smaller than a grain of sand, inside an apparatus the size of a small refrigerator, orbiting 250 miles above Earth. The experiments produce scientific data about quantum phenomena that cannot be studied any other way. They do not produce anything useful at scale. The hardware cannot cool down a cup of coffee. It cannot cool down a computer chip. It can only cool a tiny cloud of specific atoms for a tiny duration, and that is the limit of what current technology allows. But it is the coldest temperature ever measured anywhere, by humans, by nature, by any process known to science. It exists in a facility that humans built, launched and maintain in orbit around Earth, doing research that will eventually feed back into applications that today cannot be predicted. Quantum computing depends on ultra-cold atoms. Precision atomic clocks depend on them. Gravitational wave detectors benefit from the techniques used to generate them. The Cold Atom Laboratory is not an exotic curiosity. It is a proving ground for technologies that will be important in the decades to come. And in a broader sense, It is proof of how much progress human engineering has made against the thermal problem. In less than a century, humans went from not understanding vacuum thermodynamics well enough to keep cosmonauts alive during re-entry, to producing temperatures orders of magnitude colder than anything the universe produces naturally. The thermal environment of space has gone from a killer to a laboratory. Every thermal engineer who has worked on any of this will give you the same warning, though, when asked about the big picture. Ask any thermal control engineer what they've learned from decades of designing spacecraft, and they will tell you that space is not cold. Not in the way the phrase is usually meant. Space is merciless. It is an environment that punishes every mistake immediately and completely, with no margin for error, no opportunity for correction, no forgiveness for oversight. The dominant failure mode on a spacecraft is almost never freezing. It is overheating. Every craft humans have ever flown has had to fight harder to shed its internal heat than to ward off the cold. Every craft has radiated its waste heat through surfaces exposed to the vacuum, and every craft has had to balance the inward flow of stellar heating against the outward flow of its own thermal emissions. When the balance fails, the failures are catastrophic. The space shuttle's radiator doors had to open, or the crew cooked. The space station's ammonia loops had to work, or systems shut down. Webb's sunshield had to deploy, or the mission died. Parker's shield had to hold, or the probe vaporized. Philae's solar panels had to charge, or the lander froze. Every one of these systems was a single point of failure in a vehicle that could not afford any. The cold of space, the 2.7 Kelvin background, the deep frigidity that movies show as the immediate killer, is almost never the direct cause of a spacecraft's death. It is a backdrop. It is the passive environment in which the active engineering either works or does not. The cold does not rush in to freeze a damaged spacecraft. The cold simply exists, radiating inward at its slow, steady rate, while the spacecraft's own thermal systems either manage the balance or lose it. The merciless part is what happens when the balance is lost. There is no atmosphere to slow the process. There is no water nearby to buffer a temperature swing. There are no rescuers within reach on any reasonable timescale. A spacecraft with failed thermal control gets hotter or colder, steadily and inevitably, until something inside breaks. Then the rest breaks in sequence. Then the crew, if there is one, has to evacuate or die. The engineering that holds this off is some of the most beautiful in all of space technology. Heat pipes that move energy silently, radiators that glow in the infrared, sized precisely for the heat load, insulation blankets that reflect 99% of thermal radiation, sunshields that drop hundreds of degrees across layers of plastic, cryocoolers that run for decades without moving parts wearing out, passive orbits that hold spacecraft in permanent alignment with cold sky. All of it exists because the alternative is dying in a quiet, inexorable way, hours after something small goes wrong. For the crews who fly these vehicles, the thermal story is usually invisible. Astronauts aboard the International Space Station do not think about ammonia loops unless an alarm goes off. They do not track radiator panel angles unless flight controllers tell them to. The system works because thousands of engineers and operators have tuned it to work, and it runs in the background silently, keeping the internal environment livable, while the external environment tries constantly to kill everyone aboard. What the crews do think about increasingly is what comes next. The current era of spaceflight is the era of staying close to Earth. Low orbit, lunar rehearsals, Mars in the planning stages, the engineering of thermal control scales painfully as missions get more ambitious, and the bigger the ship, the worse the problem becomes. The first crew to leave the inner solar system will carry with them every lesson the thermal engineers have learned. The first crewed mission to leave Earth-Moon space for more than a few weeks will be a hard mission. Most of the attention will go to propulsion, to life support, to radiation shielding, to the physiological challenges of long-duration microgravity. The thermal story will be quieter, but it will be doing as much work as any of those systems, and it will be what keeps the crew alive between the dramatic moments. A crew on a 6-month coast to Mars will be living inside a vehicle that is rejecting tens of thousands of watts of waste heat every second. Radiator panels will be deployed outside the hull, rotating to track the ideal angle against the star. Fluid loops inside the cabin will carry warmth from electronics and from the crew's own bodies to heat exchangers. The heat exchangers will hand the warmth off to external coolant, which will flow to the radiators and glow away as infrared. The whole system will work continuously for the entire trip, and if it fails in a way that cannot be repaired in flight, the crew will not reach Mars alive. At Mars, the vehicle will enter orbit or land, depending on the architecture. Surface operations will involve a habitat drawing power from a fission reactor, radiating its own waste heat to the Martian sky, running heaters at night to keep the crew warm through -130-degree cold snaps. The reactor and the habitat will share thermal responsibilities, each balancing its own thermal loads, connected by power cables and isolated by distance for radiation protection. The return trip will be the same problem in reverse. Another 6 months of coast, another 6 months of radiator panels tracking the star and fluid loops carrying warmth. The crew will return to Earth having spent more than a year living entirely inside engineered thermal environments, and the thermal engineers back home will log every anomaly, every transient, every deviation from predicted performance for analysis. If the mission goes well, the lessons will feed into the next mission, bigger ship, farther destination, more crew. The surface-to-volume trap that makes big ships harder to cool will push radiator designs toward configurations that have never been flown before. Deployable structures measured in thousands of square feet. High-temperature radiators running at hundreds of degrees to shrink panel area. Heat pumps cycling fluids to push waste heat up in temperature before rejection. A Crude Jupiter mission, if it ever flies, will carry radiator fields larger than football fields. A crewed mission to Saturn's moons, even farther out. And a hypothetical interstellar mission, still decades or centuries away at minimum, will face the opposite problem: too cold. Not enough waste heat to keep the ship functional during the long coast between stars. The physics never changes. Heat leaves a spacecraft only by radiation, slowly, one photon at a time. Getting rid of heat is hard. Holding on to heat is hard. Balancing the two, across years of mission time, across thousands of miles of interplanetary space, across hardware that has to work without repair, is the deepest engineering problem of spaceflight. The cold of space is real. It is everywhere. It sets the background against which every spacecraft operates and against which every failure is measured. But it is not what kills spacecraft. What kills spacecraft is the mismatch between what the vehicle generates and what it can shed, between what the environment delivers and what the thermal system can absorb. For the first crew to really go deep, that mismatch will define the mission. The propulsion will get them moving. The life support will keep them breathing. The radiation shielding will keep their cells intact. The thermal control system will keep them from cooking in the dark. And long before the first of those crews reaches whatever destination humans finally commit to, the thermal engineers will have quietly done the hardest work in the program. They will have drawn every line, sized every panel, modelled every failure mode, and handed the completed design to the crew who will trust it with their lives. Space is not cold. Space is merciless. And the engineering that makes humans survive out there is the quiet, precise, relentless work of balancing heat, photon by photon, across the longest journeys any living thing has ever attempted. The next crew is watching,